All right, let's talk about something that's literally all around us, but we almost never notice it. It has zero moving parts, but it's the quiet, humming heart of our entire electrical world. We're talking about the transformer.
Just take a look at this. This is our electrical grid. It's this colossal web that generates unbelievable amounts of power, often hundreds of miles away from where you and I actually use it. It's a true marvel of engineering. But, it also presents a really fundamental problem.
So how in the world do you take that raw, super high voltage power from a power plant and tame it, turn it into the safe, predictable electricity that charges your phone without, blowing it up? Well, the answer is a brilliantly simple device, the transformer.
So let's break down what it is. At its heart, a transformer is basically an energy translator. It takes electricity in at one voltage and spits it out at a completely different voltage, all without changing the frequency. It's tough, it's durable, and it's the main reason that alternating current, or AC, won the famous War of the Currents way back when. Okay, so how does the static box pull off such a critical job? Well, the secret isn't mechanical at all. It's magnetic.
It all comes down to a principle called electromagnetic induction. And it sounds complex, but it's actually pretty cool. When you run an alternating current through a coil of wire, that's the primary winding, it creates a constantly changing magnetic field. This magnetic field is then channeled through a core over to a second coil of wire, the secondary winding, where it works its magic and induces a brand new electrical current. It's like magic.
And here's the truly brilliant part: how it controls the voltage. The secret isn't some complicated piece of machinery. It all comes down to simple counting. The ratio of the number of turns of wire in that first coil compared to the number of turns in the second coil, that's it. That ratio dictates exactly how the voltage will change. You want higher voltage, you put more turns on the second coil. You want lower voltage, you use fewer turns. It's just beautifully, elegantly simple.
And this one simple principle gives us the two absolute workhorses of the entire grid. At the power plant, you've got these massive step-up transformers that crank the voltage way up for efficient long-distance travel. Then, as that power gets closer to your neighborhood, a whole series of step-down transformers, like the ones you see on utility poles or in those green boxes on the sidewalk, safely bring the voltage back down for use in your home. So now that we know how it all works, let's pop the hood and see what's inside. What are these things actually built from?
It doesn't matter if it's the size of a car or the size of your thumb. Every power transformer is really built around three essential things: a core to guide the magnetic field, windings to carry the current, and some kind of system for insulation and cooling to keep the whole thing from melting down. The core is basically a superhighway for the magnetic field. Its job is to make sure as much of that field as possible gets from the first coil to the second one. And it's not just a solid block of metal. It's actually made of these really thin, stacked layers of a special type of steel called CRGO. This layered construction is absolutely crucial for fighting off a type of energy waste called eddy current. And then you have the windings. These coils are where all the action happens. They're usually made from copper because it's such a great conductor of electricity, though sometimes you'll see aluminum in smaller ones to save on cost and weight. This is the spot where electrical energy becomes magnetic energy and then gets turned right back into electricity again. And all this energy transfer generates a ton of heat, which has to go somewhere, right? This is where engineers have to make some pretty important choices. Those big transformers you see outdoors are usually filled with a special mineral oil. It's a fantastic insulator and coolant. But for indoors, say in a big office building, you'll often see dry-type transformers that just use air to cool down. It's all about minimizing the fire risk. Now, transformer isn't a one-size-fits-all kind of thing. They come in this incredible variety, with each one specifically tailored for its job.
As you can see here, there's a whole family tree of transformers. We've talked about voltage level. That's your basic step-up and step-down types that run the grid. And we just covered cooling method, the difference between those big oil-filled units and the air-cooled dry types. But they're also sorted by purpose. A giant distribution transformer on the grid is a world away from the tiny pulse transformer that precisely fires your camera flash or radar system. And, this is a big one, they're classified by phase. The power that comes into your home is typically single-phase, which uses a simpler transformer. But to run the heavy-duty machinery in a factory, for that, you need the massive power delivered by a three-phase or polyphase transformer, which is a whole other beast entirely.
So, we've seen how they work, we've seen what they're made of, but in a world that's so focused on energy, probably the most important question is, how efficient are they really?
And the answer is, they are unbelievably efficient. Large power transformers can be over 99% efficient, which makes them one of the most efficient machines humankind has ever built. But, and this is a really big but, 1% of a gigantic number is still a really big number. That wasted energy adds up. Transformer energy losses really come in two main flavors. First, you have core loss. Think of this as a constant energy tax that gets paid just to keep the core magnetized 24/7, whether you're using power or not. Then you have load loss. This is heat lost in the windings, and it gets worse the more power you try to pull through the transformer. And this is where our modern world really changes the game. See, transformers were designed for a nice, smooth wave of electricity. But our modern electronics, computers, phone chargers, LED lights, they draw power in these short, abrupt, jagged bursts. This creates what engineers call dirty power, or harmonic distortion. It's like sending choppy waves through a system designed for a smooth river, and it puts a ton of extra stress on transformers, causing them to heat up and waste even more energy.
So to fight this, engineers came up with a rating system called the K-factor. A standard transformer might have a K-factor of 1, but for an office building that's jam-packed with computers, you might need a specially built K13 or even a K20 transformer, one that's designed to handle all the extra heat from that harmonic distortion.
And the innovation is not stopping there. To fight those constant core losses, engineers are now creating entirely new materials. Transformers built with amorphous metal cores, which is a kind of metallic glass, can slash those no-load losses by a staggering 60 to 70%. That saves a massive amount of energy over the life of the device.
Which really brings us to our final question. The transformer has been the cornerstone of our world for more than a century. But as we face new energy challenges and the unique demands of our digital age, this unsung hero is evolving. The next generation of transformers will have to be smarter, more efficient, and more resilient than ever before. That quiet hum of the transformer, well, that's the sound of our world running, and the story of its future is definitely still being written.
Let's study more and like, share, and subscribe for such more content. And comment something you want to learn.